Welcome to this comprehensive lesson on arc length. Arc length is one of the most practical and important concepts in geometry, and today we're going to explore exactly what it means and why it matters. So, what exactly is arc length? Arc length is simply the distance along the curved line that forms a portion of a circle's circumference. Think of it as measuring the length of a curved path rather than a straight line. Here we have a circle. When we talk about arc length, we're referring to the distance along this curved segment of the circle's edge. This curved distance along the circle's edge is what we call the arc length. It's important to understand that this is different from the straight line distance between the same 2 points. Notice the difference. The chord length is the straight line distance between the 2 endpoints, while the arc length follows the curved path. The arc length is always longer than the chord length for the same 2 points. Here's a helpful way to think about arc length. Imagine you have a slice of pizza. The arc length would be like measuring the length of the crust along the curved edge of the slice. Throughout this video series, we'll cover all the essential concepts you need to master arc length. We'll start with the key concepts like central angles and radius, then learn the formulas for both degrees and radians, work through detailed examples, and explore real-world applications. By the end of this series, you'll have the confidence and skills to tackle any arc length problem, whether it's for homework, tests, or real-world applications. So let's dive in and start building your understanding of this fundamental geometric concept. Before we can calculate arc length, we need to understand 3 fundamental concepts that work together in every circle. These are the building blocks of arc length calculations. First, let's define what an arc is. An arc is simply a curved segment of the circle's circumference. Think of it as a portion of the circle's edge between 2 specific points. Next is the central angle. This is the angle formed by drawing 2 straight lines from the center of the circle to the endpoints of our arc. The central angle determines how large or small the arc will be. Finally, we have the radius. The radius is the distance from the center of the circle to any point on the circle's edge. Notice that both lines we just drew are actually radii of the circle. Now you can see how these 3 concepts work together. The arc is the curved distance we want to measure. The central angle determines the size of that arc, and the radius tells us how far we are from the center, which affects the arc's actual length. Understanding these 3 concepts is essential because they form the foundation of every arc length calculation. In the next section, we'll see exactly how to use these concepts in our first arc length formula. Now we'll explore the arc length formula when the central angle is measured in degrees. This is one of the most commonly used formulas in geometry. We start with a circle that has a center point and a radius r. The radius is the distance from the center to any point on the circle. When we draw 2 radius lines from the center, they form a central angle, which we call theta. This angle determines how much of the circle's circumference we're measuring. The arc length, which we call L, is the distance along the curved edge of the circle between these 2 radius lines. This is what we want to calculate. The arc length formula when the angle is in degrees is L equals theta over 360 multiplied by 2 pi r. This formula might look complex, but it's actually quite logical. Let me break down each component. L represents the arc length we want to find. Theta is our central angle measured in degrees, and r is the radius of our circle. The key insight is that theta over 360 gives us the fraction of the complete circle that our arc represents. Since a full circle is 360 degrees, this fraction tells us what portion we're measuring, and 2 pi r is the formula for the complete circumference of the circle. So we multiply our fraction by the total circumference to get just the arc length we want. For example, with our 90-degree angle, we get 90 over 360, which simplifies to 1/4. This makes perfect sense because 90 degrees is exactly 1/4 of a full 360-degree circle. You can see this visually. Our highlighted arc is exactly 1/4 of the circle's circumference. The formula gives us 1/4 of the total circumference, which is exactly what we want. This formula works for any angle, whether you have 180 degrees, which is half the circle, or 270 degrees, which is 3/4. The formula will give you the correct arc length every time. Remember, the arc length formula for degrees is L equals theta over 360 times 2 pi r. This formula connects the central angle to the portion of circumference, giving us a powerful tool for solving arc length problems. Now we'll explore the arc length formula when the central angle is measured in radians. This version of the formula is actually much simpler and more elegant than the degree version. Let's start with our familiar circle setup. We have a circle with center point, radius r, and an arc with central angle theta measured in radians. Here we have our radius r, central angle theta in radians, and the arc length L that we want to find. When the central angle theta is measured in radians, the arc length formula becomes simply L equals theta times r. Notice how much simpler this is compared to the degree formula. This formula is remarkably simple because radians are defined in a way that directly relates to arc length. To understand why the radian formula is so simple, let's look at a unit circle, a circle with radius equal to 1. When we have a central angle of exactly 1 radian, the arc length equals the radius. This is actually how a radian is defined. In a unit circle, when theta equals 1 radian, the arc length also equals 1, which is the same as the radius. Using our formula L equals theta times r, we get L equals 1 times 1, which equals 1. The formula works perfectly. Remember this important conversion. 2 pi radians equals 360 degrees. This means pi radians equals 180 degrees, and 1 radian is approximately 57.3 degrees. So remember, when working with radians, the arc length formula is simply L equals theta times r, where theta is in radians. This direct relationship makes radians the preferred unit for many mathematical calculations involving circles. Now we'll work through our first example to see how the arc length formula works in practice. We have a circle with a radius of 5 centimeters and a central angle of 60 degrees. We need to find the arc length, so we'll use our formula for degrees. Remember, L equals theta over 360 degrees times 2 pi r. Step 1, we substitute our values into the formula. Theta equals 60 degrees and r equals 5 centimeters. Step 2, we simplify the fraction. 60 divided by 360 equals 60 over 360, which simplifies to 1 over 6. Now we continue with our calculation. Step 3, we multiply the constants. 2 pi times 5 equals 10 pi. Step 4, we calculate the final result. 1 over 6 times 10 pi equals 10 pi over 6, which simplifies to 5 pi over 3. Converting this to a decimal approximation, 5 pi over 3 is approximately 5.24 centimeters. So our arc length is 5.24 centimeters. This represents the distance along the curved path of our 60-degree arc. This example demonstrates the key steps. Substitute the values, simplify fractions, perform the arithmetic, and express the final answer with appropriate units. Now we'll solve our second example using radians instead of degrees. This will demonstrate why many mathematicians prefer working with radians for circular measurements. We have a circle with radius 8 inches and a central angle of pi over 4 radians. We need to find the length of the arc created by this central angle. First, let's recall the arc length formula when the central angle is measured in radians. This formula is beautifully simple. The radian formula is L equals theta times r, where L is the arc length, theta is the central angle in radians, and r is the radius. Now let's substitute our values into this formula step by step. Step 1, substitute our values into the formula. We have theta equals pi over 4 radians and r equals 8 inches. Step 2, multiply the values. Pi over 4 times 8 equals 8 pi over 4, which simplifies to 2 pi. Finally, let's convert this to a decimal approximation for a practical answer. Step 3, convert to a decimal approximation. 2 pi is approximately 2 times 3.14159, which equals approximately 6.28 inches. Notice how much simpler the radian formula is compared to the degree formula. This is because radians are the natural unit for circular measurements, making calculations more straightforward and elegant. Therefore, the arc length is approximately 6.28 inches. This demonstrates the power and simplicity of using radians in circular calculations. Arc length isn't just a theoretical mathematical concept. It has numerous practical applications across many professional fields and even in our daily lives. Understanding how to calculate arc length helps engineers design structures, astronomers track celestial bodies, and navigators determine distances. In engineering, arc length calculations are crucial for designing curved structures like bridges and arches. When engineers design a curved bridge, they need to know the exact length of the curved roadway to calculate materials needed and structural loads. In astronomy, arc length helps calculate the distances that planets and other celestial bodies travel along their orbital paths. This is essential for predicting positions, planning space missions, and understanding orbital mechanics. Navigation systems use arc length to calculate distances between 2 points on Earth's surface. Since Earth is approximately spherical, the shortest distance between two cities follows a curved path along the Earth's surface, not a straight line through the planet. Even in everyday life, understanding arc length helps us estimate distances along curved paths. Whether you're walking along a curved sidewalk, driving around a circular track, or measuring the length of a curved garden border, arc length calculations give you accurate distance measurements. As you can see, arc length calculations are everywhere around us. From the massive scales of planetary orbits to the everyday curves we encounter, the mathematical principles we've learned provide the foundation for solving real-world problems. This demonstrates why understanding mathematical concepts like arc length is so valuable. They give us the tools to measure, design, and navigate our curved world. We've covered everything you need to know about finding arc length. The two essential formulas are the foundation of arc length calculations. Remember, when your central angle is given in degrees, use L equals theta over 360 times 2 pi r. When the angle is in radians, the formula simplifies beautifully to just L equals theta times r. Here are the key points to remember as you practice. Always check whether your angle is in degrees or radians first. Remember that arc length measures the curved distance, which is always longer than the straight chord distance. And most importantly, practice with different values to build your confidence. The best way to master arc length is through practice. Try creating your own problems with different radius values and angles. Work through real-world applications like finding distances along circular paths or calculating arc lengths in engineering problems. If you found this video helpful, please give it a thumbs up and let me know in the comments what other math topics you'd like to see. Don't forget to subscribe and hit the notification bell for more math tutorials. Keep practicing and remember that every expert was once a beginner.